Hi everyone. Today's lesson will review hemodynamic pressures and hemodynamic calculations. It's probably been a while since you put your eyes on it, so I thought it would make for a good review. We'll begin by looking at the anatomic names of the vasculature and the hemodynamic loop. Starting here at the alveoli, we've got of course the pulmonary capillary bed, which allows blood to move into the pulmonary vein. From the pulmonary vein, we'll enter the left atrium and left ventricle. The left ventricle contracts, pushing blood through the pulmonic valve into the aorta. From the aorta, we have arteries to smaller arterioles, and then into the systemic tissues, known as the systemic capillary bed, where we have metabolism occurring. So we have gas exchange occurring here. Blood continues moving into the venules, collecting into the veins, into the larger vena cava, which then moves into the right atrium, the right ventricle. Right ventricle contracts, pushing blood through the pulmonic valve into the pulmonary artery. So the vessel leaving the heart's an artery, and then back again to pulmonary capillary where gas exchange takes place again. This drawing shows the same hemodynamic loop. I just put the pressures in their respective places, and as a quick review, all of your blood pressures, of course, should be in millimeters of mercury or torr. But if you ever see or have a need to convert to centimeters of water, then you would multiply by 1.36. That would be your conversion factor. If for some reason you have hemodynamic pressures in centimeters of water, and you'll need to convert them back to millimeters of mercury or torr, then you would divide by 1.36 using the same conversion factor. So always put your eyes on the unit of measure being used in hemodynamics, making sure that you're reading it properly with the proper unit of measure. Alright, just to plug in all of our values, we'll go back here to the pulmonary capillary bed. This is supposed to be a pulmonary artery catheter or a Swan-Ganz catheter, which is why it looks that way. Currently you don't see a cuff, meaning the cuff is deflated, so we're registering the pulmonary artery pressures, normally around 25 systolic over 10 diastolic. If we average those pressures, they average to about 15. We'll look at calculations later, but these are just giving kind of the rundown of the numbers. If I were to inflate the cuff, then we're no longer reading pulmonary artery pressures behind the cuff. We're reading pressures in front of this cuff, which is the pulmonary capillary wedge pressure. That's also sometimes referred to as pulmonary artery occlusive pressure. So PCWP or PAOP, either way. Normal wedge pressure around 4 to 12 millimeters of mercury, middle number of about 8. The pulmonary capillary wedge pressure is very close to the pulmonary vein pressure, which approximates the left atrial pressure. Once blood is ejected from the left ventricle, we achieve a high systolic of 120, our diastolic approximately 80. Again, to average, take your systolic, add 2 diastolics, divide by 3, so we'll have a mean arterial blood pressure of approximately 93 torr. As we move from the arteries down into the arterioles, pressure decreases to an average of approximately 30 torr. For tissue perfusion in the systemic capillary bed, approximately 20 torr, and in the venules, approximately 10. So these are just very easy numbers to remember, 30, 20, 10. And then as we move back to the vena cava, we'll have our central venous pressure of approximately 2 to 6 torr, which approximates the right atrial pressure, which is the filling pressure of the right heart, as blood is again moved into the pulmonary system. Okay, just a quick review. This gets a little bit more difficult. This looks at calculations. So as a header, I have calculating systemic and pulmonary vascular resistance. And when we're looking at vascular resistance, Essentially what we're doing is taking the delta P, or the change in pressure, whatever system we're looking at, whether it be the pulmonary system or the systemic. Take your delta P in the numerator, and then in the denominator put your change of flow. V dot is flow, so we have pressure over flow, and pressure over flow gives us resistance. So to determine your change in pressure, I have the pulmonary vascular resistance calculation here. We'll take the high pressure and we're going to subtract the low pressure. So your high pressure in this circuit is the pulmonary artery pressure, and we're going to use the mean, which is about 15. Okay, so there's your high pressure. Subtracting the low pressure, your low pressure in the pulmonary circuit would be your pulmonary capillary wedge pressure, also known as pulmonary vein or the left-sided atrial filling pressure. So PVR is your delta P, high minus low, over flow, and your flow will be your cardiac output. So that's pretty easy. So the resistance through this pulmonary circuit is the high minus the low divided by flow, cardiac output. For the systemic circuit, we'll take the high pressure, which is your mean arterial blood pressure, which you see here in the numerator. That's the high pressure, subtract the low. The low will be your CVP. That gives us our delta P. High minus low over flow, your flow being cardiac output. Lastly, I have some examples of equations, just two to look at. The first one is calculating pulmonary vascular resistance, and I've also converted it to dynes. And the second is calculating systemic and converting it to dynes. So I'm taking the same numbers we've looked at, high pressure of 15, low pressure of 8, coming from our mean PA and our pulmonary capillary wedge pressure, dividing it by cardiac output, gives us 1.4. I simply dropped our unit of measures down here, millimeters of mercury over liters per minute. So there's millimeters of mercury over liter over minute. And then to convert to dynes, you multiply by 80. So 1.4 times 80 gave us 112 dynes. For systemic vascular resistance calculation, high minus the low, so there's 93 minus 4 over flow, 5 liters a minute, equals 89 over 5, 17.8. Dropped your unit of measure, millimeters of mercury per liter per minute. Multiply by 80, giving us 1,424 dynes. If you have any questions, please let me know. Thank you.